So go ahead.
Thank you, Mario. And thank you, Jennifer, for both of you for the invitation. It's nice to see you again so soon. Okay, so this is, sorry. Okay, this is based on this paper called called the same as the talk, and this is joint work with Mario Eudave and Enrique Ramirez Lozada. So the subject of this talk will be 1-1 knots, and let me remind you what is an 1-1 knot. So we are thinking about knots in S3, and we are taking the genus 1 Higar splitting of S3. So a 1-1 knot will be a knot which admit a 1 bridge position with respect to this standard torus. So in this picture, you can see such an example of that type of knots. And so these knots are interesting because they belong to the family of tunnel number 1 knots, and they contain rational knots and satellite tunnel number 1 knots. So here, this is just a little reminding of the construction of the satellite tunnel number 1 knots by Morimoto and Sakuma, a little picture of the rational knots. And well, tunnel number 1 knots are knots which admit an arc, so that the graph given by the arc union the knot, the complement is a handle body of genus 2. Okay, and so the other ingredient of this talk is the genus of a knot. But let me say that we need two kind of genera for a knot: the orientable genus, as all of you recall, is the least genus of any cipher surface for the knot, and there is this kind of non-orientable genus, also known as the cross-cut number of the knot. And so we'll be talking about those two types of genera for a knot. So combining genus and knots and 1-1 knots, we have the following results. So genus 1-1 knots have been classified by work of Matsuda and Charlemagne. And these knots are, there are all tunnel number 1 genus 1 knots. All 1-1 knots of genus 1 are tunnel number 1 genus 1 knots. So the 3 sets I showed in the previous slide are the same, okay? And later, Enrique Ramirez and Luis Valdez, they classified 1-1 knots that bound Klein-Borel. So they classified those knots. And later, in Mario, Enrique, and myself, we classified genus 2 1-1 knots. And well, just recently, we gave a classification of the, for any genus G knot which admit a 1-1 knot. So this is briefly the history of this problem. And so I want to say a few words about the classification of genus 2 1-1 knots, just to give you an idea of the general case. So in that classification, we defined this what we call the vertical sum of 2 1-1 knots. So in this picture, we see 2 1-1 knots, K1 and K2, the green one and the blue one. And so what we do is we kind of put them in a very nice position, because they have this very nice position, 1-1 position. And what we do is we just take an arc of the knot K1, and another, well, we remove a little arc of, so because these knots are 1-1 knots, we can think of them as being in a product torus cross I in that region. And so we can think that they have in this product region, they have a maximum and a minimum. So the vertical sum that we are defining is with respect to a minimum of one of those nodes and a maximum of the other node. And we just join them by two arcs that do not intersect any, that do not introduce any maximum or minimum with respect to this product region. So that is a vertical sum of two 1-1 nodes. And when we do that, the new node is again a 1-1 node. So in the genus 2 case, we were able to classify such nodes into the following type of nodes. So a genus 2 1-1 node will be a vertical sum of two rational genus 1 nodes, or two rational satellite genus 1 nodes, or maybe one can be a satellite genus 1 node and the other one is a rational genus 1 node, or both can be cross-cut number 2 rational nodes, or this other case says that one of the 1-1 nodes may be a trivial node in certain position, and the other node might be a rational genus 1 node, or a satellite genus 1 node, or another trivial node in certain position. So in this case of genus 2 1-1 nodes, we see that, well, they are like combination of genus of 1-1 nodes of a smaller genus. Well, of genus 1 rational nodes, or satellite nodes, or cross-cut number 2 rational nodes. And so let me show you some other pictures of the cases, or some of that illustrate these cases. So in this picture, K1 is both are rational genus 1 nodes. Here we have a combination, a vertical sum of a satellite genus 1 node and a rational genus 1 node. And here is an example of where both summands are cross-cut to 1-1 nodes. So I was, as I was saying, we because we have 1-1 nodes, we can, put these nodes with respect to this torus cross I region in S3 in such a way that outside the product region, we just have an arc of the node, and in the other region, we just see an arc of the node, and in the product region, we just see well, the rest of the node, but without maximum or minimum with respect to to a height function. And so this, in words, this is what it is saying. So this is the trivial arc, a trivial arc that can be pushed onto this torus, and this other trivial arc can be pushed into this torus, and well, we have the rest of the node grabs around this region without critical points with respect to this height function. And so given this product region, this height function, now if we have an essential cipher surface for the node, well, we have this lemma that, well, we used for the classification of genus to 1-1 nodes. And well, what this lemma is saying is that with respect to that height function, the essential cipher surface inside the product region, the surface, we only see saddle points. There are no minima or maximum points, critical points inside. And the other characteristic is that outside the product region, the surface, the pieces of surface that we are going to see are just this kind of annuli and these other little pieces that are called canceling disks. And also, this lemma let us count how many saddle points we see in this product region. Okay, so this was very useful when we classify the genus 211 knots. But when we were trying to do the general classification, well, we had some trouble because of the annuli outside the product region. Okay. Okay. So these are the kind of the saddles we are gonna see in the product region for the surface, for the cipher surface. Okay. So what we did, a key step to get rid of this annuli that show outside the product region was to perform what we call surgery of F along annuli. So we are considering cipher-oriented surfaces for the knot. And so since the cipher surface is oriented, and so every time we have a torus level, and that torus level intersects the cipher surface into two curves that with opposite orientations. So we know that these curves are parallel on this torus level. So they co-bound an annulus. And so if in that annulus does not contain any other curve of intersection of the surface with the torus level, so we perform what we call annulus surgery of F. So we just cut along the curves, and we take a copy of this annulus and we cap off on the top, on the bottom, and we obtain this new surface. And we get rid of these curves of intersection that with opposite orientation. So we do that for every time we see these kind of intersections. And so we were able to modify the previous lemma for a better lemma that says that given an oriented cipher surface of minimal genus for K, after a finite number of such annuli surgery, we obtain a minimal genus cipher surface with the same characteristics as before, that in the product region there are only saddles. And well, we have after doing these surgeries, we were able to get rid of the annuli, all the annuli outside the product region. Moreover, every time this new surface intersects a level torus, the curves will have the same orientation. Okay. And so when a surface satisfies those conditions, we call that surface, we said it is a simple cipher surface. So just rephrasing the lemma, it says that every 1-1 knot has a simple minimal genus cipher surface. Okay, so this was useful because after a number of many lemmas, we were able to show that a simple minimal genus cipher surface for a 1-1 knot can be isotoped in such a way that in the product region, instead of having all those 4 types of saddles, we only have these 2 types of saddles. Okay, so saddles that join an arc with itself, or saddles that join an arc with a curve. Okay, and so it simplifies a lot the structure of the cipher surface with respect to this torus cross-eye structure. Okay, and well, we also can, we have this control of how many type of saddles we have, and it's just the total amount of saddles is twice the genus of the cipher surface. Okay. So here is the description of 1-1 knots of genus G that we gave. So given a knot, a 1-1 knot, and a minimal genus G simple cipher surface for a knot, for that pair, we can assign a collection of slopes, a collection of numbers, GI, such that when you add them up, we obtain the genus of the knot, and we obtain a collection of surfaces so that the boundary of those surfaces are 1-1 knots of genus GI, such that when we perform the vertical, so that the big knot, the given 1-1 knot, can be obtained by vertical sums of these knots. And we also can say that if the slope satisfies this condition, so the knot, the 1-1 knot, is a satellite knot of winding number 0. So I prepared a little sketch of the proof. So this picture is meant to be a cartoon of a 1-1 knot and a cipher surface, a simple minimal cipher surface for the knot. So like the bottom is, say, this whole region is the torus region, and so because the cipher surface is simple, this arc can be pushed into, to say this bottom part is torus cross 0, and the top part is torus cross 1. So this is, and you see, we only have 2 types of saddles. So we start from bottom to top. So here is a saddle that joins an arc with itself, giving rise to an arc with a curve, and so on. You see another saddle that joins the arc with itself, and so on. So this is what we have. And so the next step is to detect torus levels so that the cipher surface intersect only in one arc. Like, well, that's another picture. So of course we have the bottom and the top, where the cipher surface just intersects this arc. So we detect this other torus level where we just see an arc and so on. And so we can cut the surface along these torus, all these torus levels, and so these pieces knots. So we produce new knots, and these knots are again, we produce these surfaces that are these, whose boundaries are knots, which are 1-1 knots. And so in the lemma, you see where it says that we obtain a collection of slope, a collection of numbers, and a collection of surfaces, so that the knot is given, is obtained by this vertical sum. So this is, so the collection of slopes, it refers to this, to these curves that appear in each between each two consecutive levels, where you just see arc of intersections of the cipher surface with these torus regions. So this is basically, it's very sketchy idea of the proof. And so how do we recover the original knot? Well, just by taking this, gluing back them, and gluing back them these pieces is just a vertical sum. Okay. So this, the pieces, this will be a genus. Well, the whole thing was like a 1, 2, 3, 4, a genus 4 cipher surface. So this piece is a genus 1, 1, 1 knot. This is a genus, so in this picture, we may claim that this piece is a genus 1, 1 knot, but probably this thing, let me say it better reading the proposition. So once we have these pieces, we just know that these knots is these surfaces are of genus, say this 1, 1, and 2, but we can say further about the pieces obtained in the previous theorem. So so what can happen for those pieces are listed in this proposition. So each piece obtained might be a trivial knot in certain position, except for the first and the last knot obtained. It could be, each piece may be a rational genus 1, 1 knot, or a satellite genus 1, 1 knot, or this whole thing may be another vertical sum of, other pieces. And in these pieces appears knots of at most, that have at most cross-cap number 2. Okay, and so another thing we did in this project was to, since the family of 1, 1 knots contain rational knots. So what we show also in this paper was that we can obtain a rational genus G knot by a vertical sum of G genus 1 rational knots. So let me show you with an example what is how we prove this. So in this picture, you can see 4 genus 1 rational knots that are in this, this thing here. Try to picture this product region, and each genus 1 rational knot is accommodating this concentric way. And so here we take 4 genus 1 rational knots, and then we perform a vertical sum. This very concrete vertical sum that is just I don't know, very silly, just adding this trivial band between each two consecutive rational knot. And so, so what we did is just to start sliding this, starting from the inner summand. We start just sliding in this way. So we move this little piece of the surface, and it travels all around this piece, and then it ends up here, and we just isotope this for it to be, you know. And so we start, and then we slide the other summand, so you can kind of figure out that, you know, we are doing the same thing over and over. So here, repeat the operation once more, and we end up with a picture like this. And so we just end up with this final position that is not hard to see, that is a rational knot that, well, sorry. This is the final position for this example. And in the general set, we are going to end up with a position like this. These boxes here are just number of crossings given by the parameters of each rational knot. And here is again the same picture, but with the surface obtained. And this surface is precisely a minimal genus G cipher surface for the rational knot. So we just show that precisely taking G, this vertical sum of G genus 1 rational knot give us a rational knot of genus G. That's all what I wanted to say. Thank you for your attention.
Okay, thank you very much. So are there any questions? No. No questions? Okay. Thank you very much.